All right, let's do another example. This time we have tangent. Tangent of 75 degrees. 75 degrees is not on our unit circle, so hopefully we can use some scratch work to write 75 as a sum of two of our angles we know. And most of the times I like to work backwards, like 75 degrees. I'm just going to subtract something that I know is on the unit circle, like 45 degrees. So that gives us 30 degrees. Perfect. 45 and 30 are on the unit circle. So this tells us that 45 degrees plus 30 degrees is 75 degrees. So that gives us a sum that we can use, and we can use one of our formulas. So we can rewrite tangent of 75 degrees as tangent of 45 degrees plus 30 degrees. And then we come back. Let me see if I can fold this paper. All right, so we come back. We can use our formulas. The one for tangent with addition. So that says we need to take tangent of our first angle, add it to tangent of our second angle, divide it by 1 minus tangent of the first times tangent of the second. Okay. All right, so let's go ahead and write down those values. Tangent of 45 degrees is just 1. All right, plus tangent of 30 degrees. We probably have to do a little division, but it's 1 over root 3 divided by 1 minus 1 times 1 over root 3. Okay, and we're going to simplify this by getting a common denominator on the top and the bottom. All right, so on the top, my denominator is going to be root 3. And so I had to multiply this one by root 3. On the bottom, common denominator is going to be the same. That will be helpful. Over here, I'm going to have to do a root 3 minus 1. All right, these are the same, so when you multiply by the reciprocal, they're going to cancel. So we're going to have root 3 plus 1 over root 3 minus 1. Okay. All right, let's look at the next one. Sine of pi over 12. So if you don't like thinking about the angles in radians, you can always convert this into a degree if you want, and maybe that's easier for you to work with. That's fine. I'm going to stick with radians though. Get some scratch work. I noticed that pi over 12 is really small, so I'm probably going to be subtracting things. So I'm just going to take a wild guess, maybe pi over 3 minus pi over 4. Let's see, common denominator of 12. Four minus 3 is 1, so pi over 12. That's exactly what it was. Perfect. Okay, so we can rewrite sine of pi over 12 as sine of pi over 3 minus pi over 4. All right, and so that means we have subtraction, so we want to use the sine formula for subtraction. All right, let's try to fit this all on the screen. Okay, so that means we need to take sine of our first angle times cosine of the second angle minus cosine of the first angle times sine of the second angle. All right, so that was our difference formula for sine. All right, then we just need to figure out sine of pi over 3. Well, that's root 3 over 2. Cosine of pi over 4, root 2 over 2. Cosine of pi over 3, that's 1/2. Sine of pi over 4 is root 2 over 2. Right, then we just need to multiply. Root 6 over 4 minus root 2 over 4 is root 6 minus root 2 over 4. All right, so how are we feeling about this so far? Are we getting the hang of what's happening? Okay, last one of this type. We got cosine of 99 degrees, cosine of 36 degrees, minus sine of 99 degrees times sine of 36 degrees. All right, so we first notice, oh, we got the same angles on either side of our subtraction. This one starts with a double cosine and then a double sine with a minus in between. We can match that up with one of our formulas. Cosine, cosine, well, that happens when we have a cosine sum or difference, and we got subtraction in the middle, so that tells us this is a sum formula for cosine. So we just do cosine of the first angle plus the second angle. So cosine of 99 degrees plus 36 degrees. That is cosine of 135 degrees. Perfect, 135 degrees is on our unit circle, and cosine of that is negative root 2 over 2. Okay. All right, let's look at another example. So how else we could use these sum and difference identities. Okay, so number 2 says, find the exact value of sine alpha plus beta, given that sine of alpha is 5 over 13 and cosine beta is 5 over 6 for alpha in quadrant 2 and beta in quadrant 4. All right, so this is going to be really important to us where these are located. So I'm actually going to draw out some triangles on the side that represent alpha and beta. So alpha is in quadrant 2, so I'm just going to draw these over here. All right, so we can use this triangle. Alpha is over here. And it says that sine of alpha is 5 over 13. So this side is 5. The hypotenuse is 13. And we just have to figure out the other side. All right, so we got what? 5 squared plus b squared equals 13 squared. And I got that b squared is 144, so b is 12. And you can leave it as positive 12 or you can write it as negative 12, just making sure that positives and negatives work out at the end, right? Sine is positive in the second quadrant. All right, also we know that beta is in quadrant 4, so I'm going to draw over here. And remember, when we're drawing our triangles, we always draw up or down to the x-axis. So we can represent our beta using this triangle. That's our beta. And it says cosine is 5 over 6. Well, that's adjacent over hypotenuse. All right, and then I think I'll have enough space if I do it over here. So we got 5 squared plus b squared equals 6 squared. 6 squared is what? 36? Yeah. B is the square root of 11. So this side is square root of 11. You can leave it positive and work with the negatives later. I'm going to go ahead and make it negative. All right, so this is the setup. We've drawn alpha and beta in their appropriate quadrants. We have drawn right triangles that we can work with, and we've labeled the side lengths of the right triangle. So in the next video, I'm going to show us how to actually start this problem now that we have this set up.